Hello, everybody, and welcome back to another episode of Here Comes the Boom, where we discover chemistry in explosive ways. Today, we're going to be determining the resonance energy of benzene through bomb calorimetry. Today, we will be looking at the evolution of heat in the combustion of organic compounds in constant volume conditions. This means that in these conditions, the heat will be equal to the change in internal energy for the reaction. This allows us to easier understand the compounds in the experiment. The particular reaction that we're looking at today is the reaction between benzene and cyclohexane to create CDDT, which is used in the creation of numerous compounds that are used from day to day, such as flame retardant materials and even fragrances. Here we are also interested in this because of what is called an isodemic reaction, which means that the number of bonds and the bond types are the sum of its constituent parts. With this in mind, it should also come to no surprise that the heat of combustion for CDDT, also known as the heat released when a compound is burned, should be the sum of benzene and cyclohexane. But this isn't necessarily the case. Benzene has its own resonance structures, which each in turn have their own energy, which can affect the heats of combustion. And this is precisely what we'll be looking at today. There are several very important reasons to research this. Primarily, the resonance energy that we mentioned earlier can have really heavy influences on the heats of combustion noted in the gas phase, when the compounds are more volatile. This can shed a lot of light on how resonance of other compounds can affect the properties of their polymers. Secondly, the use of bomb calorimetry allows us to test these reactions in the constant volume conditions that we want, which will help make the conditions controllable, and therefore that makes the heats of combustion significantly easier to calculate for. Finally, and as always, these experiments will help us better understand the world around us, even if we can't see it. And here we have 3D models representing cyclohexane, benzene, and CDDT. As you can see, they're all quite different, with cyclohexane having an extremely flexible structure, where benzene has an extremely rigid structure due to its double bonds. CDDT has properties present that are in both cyclohexane and benzene. However, for this reaction to occur, multiple smaller changes must happen first. In order for CDDT to be formed in its gas phase, we need to find the enthalpy changes of multiple components, such as the heat of vaporization for benzene, cyclohexane, and CDDT, as well as the combustion heats of benzene and cyclohexane. This is an important step in our research, as the total sum of all these enthalpies helps us find the negative of our resonance energy for benzene, which is then just a simple sign change away from what we're looking to find. It is really important to note that a lot of these values for combustion, vaporization, formation, and even resonance energy have literature values. But these are not always precise. Since we will not be using benzene, the heat of combustion and vaporization was found through the NIST, a very simple Google search away. This was also true for the heats of combustion and vaporization for cyclohexane and the heat of combustion for CDDT. The heats of formation for CDDT were found using the exact same software used for the modeling of the molecules. These were used to find a theoretical resonance energy for benzene as well when completely summed together. The heat of vaporization for CDDT was found in a different manner, though, using the analysis of vapor pressure. By looking at the vapor pressure for CDDT related to temperature, the slope of our line that is shown here was simply multiplied by the universal gas constant, which is 8.314, and gave us an extremely reasonable heat of vaporization. Now we can get into the meat of the experiment. In order to run this experiment, it is important to note that benzene is extremely dangerous, so we will be only working with cyclohexane and CDDT. Down at the bottom here, we have our bomb calorimeters and chemicals. These allow us to create our controlled conditions for the experiment. When working with cyclohexane, it's also important to note that it's really volatile, so it must be put into a capsule and then placed into the basket of the calorimeter. For CDDT, it is less volatile, and the liquid chemical can be placed directly into the basket. When this is done, The next step is to cut a length of wire to be our fuse, approximately about 10 centimeters. This fuse was then placed in above the basket, with the wire just touching the sample and careful not to touch the outside metal of the basket. The calorimeter was then sealed with the basket and the lid. This needed to be sealed very gently to avoid any kind of issues. In order to get our controlled conditions, the bomb then needs to be pressurized. So the bomb is then pressurized and depressurized multiple times with pure oxygen until it is primed and ready to go. In order to help control the explosion, DI water was poured into a bucket that would hold the primed bomb. Once the bomb is ready to go, it is placed into the stirrer, which you see here on the top left, and submerged in the water, where it was then hooked up to our detonator and temperature probe as seen on the right. The temperature was measured for a brief period to get a baseline, and then we pressed that red button, and you know what that means. This was repeated twice for CDDT and for cyclohexane. Now it's important to look closer at what we're investigating. The data we get out of our experiments looks a little bit like this. The graphs are relatively the same shape with similar behavior, which is extremely useful when doing the calculations that are shown later. You'll notice 5 points on the graph, where Ti is representative of the initial temperature of the bomb submerged in water. Conversely, Tf is the final temperature of the water surrounding the calorimeter post-detonation. Ta and C are the temperatures at detonation and maximum post-detonation, respectively. And finally, Tb is the temperature at 60% of the final temperature of the complete reaction. All these values become extremely critical when calculations occur. This experiment has many moving parts that rely on many calculations. It is easier to lay them out for you here. The first major calculation is finding the change in temperature. The temperature graphs shown provide values for this equation, with the R1 being the slope between the initial and detonation temperature, and the R2 being the slope between the maximum temperature and the final temperature. As we discussed earlier, Hess's law is the backbone of this experiment, and the total change in enthalpy is equal to the total sum of the changes of enthalpy in the reaction. As mentioned earlier, this allows us to find the resonance energy of benzene. Breaking this down even further, the change in enthalpy at any point in the reaction is equal to the total change in internal energy plus the change in moles of gas times the universal gas constant times the temperature. The final set of calculations expand on the last even further, where the change in internal energy is equal to the negative heat capacity of the calorimeter multiplied by the change in temperature we calculated earlier, with the total heat of combustion being the change in internal energy minus the heat of the ultimately burned fuse minus the unburned. Our data from the graphs earlier ends up looking a little bit like this. All of these temperature data points and sample sizes allow for us to find our change in temperature for the system, and lets us find our own values to find the resonance energy through Hess's law. With our changes in temperature, it finally allows us to find the heat of combustion for both cyclohexane and CDDT, which when combined with the literature values filling in our missing pieces, we can then use in Hess's law. Now you might notice if you go back a bit in the video that the heats of combustion here look a bit different than in the literature. We'll see how that affects our results. When we finally combine all of our values, it is important to average our experimental values for the heats of combustion. This way, we get a more accurate result, closer to the true value that we experimentally found. Once this lengthy calculation is done, we arrive at our final answer for the experiment, that the resonance energy of benzene is quite large at 3,279 kilojoules per mole, which we can now compare to our literature value from the beginning of the video. When we compare our experimental value to that of the literature, we find ourselves an absolutely absurd amount of error. Now, this result does not necessarily mean that our experiment was for nothing. There are many observations that we can make from this, and when we can use these observations to improve what we do in the future. When we initially hypothesized that the calorimeter would provide us a controlled environment to help identify the heats of combustion for our compounds that we studied, while this is true and allowed for our calculations to be simplified, much could have still gone wrong, from the possibility of incomplete combustion to a malfunction in the wiring setup. Many factors still affect the end data, Another observation immediately apparent is that the reaction has many complex parts, as expressed through Hess's law. The disadvantage of not working with benzene is the reliance on literature values, which vary so drastically from the experimental values. This skews the results heavily, as these are the results of myriad tests over a long period of time. Working with benzene itself, along with cyclohexane and CDDT, could have improved the results, but due to the hazardous nature of benzene, it's just not possible. Finally, both in the literature value and in our experiment, the resonance energy of benzene proved itself to be a major contributor to the heats of combustion for cyclohexane and CDDT. Thank you guys so much for tuning into this experiment, and I hope to see you all again soon.